Okay, so now it's time to conclude the polar decomposition theorem. So recall, at this point we've defined S1 on the range of root t star t by just defining it to be equal to t of v there. And we've defined the isometry S2 by picking orthonormal bases for this space right here and also the orthogonal complement of range t, and then just mapping one basis element to the other. And so now we're going to string these together, or rather add them together, to get an isometry on all of V. So for V in V, write it as U plus W with U in the range of the root and W in the orthogonal complement of the range of the root. And define S of V to be S1 of the first part plus S2 of the second part. Okay, so this will automatically define S as a linear operator, and it's now defined on all of V. We need to check that it's an isometry and that it satisfies this formula right here. So let's see. So for the first part, if we look at the magnitude squared of SV, then this is going to be S1U plus S2W magnitude squared by just the definition of S. And then since S of U1 lives in the orthogonal complement of S2 of W, S1U lives in the orthogonal complement of S2W, then we can use Pythagoras to split this. And then we know that S1 is an isometry on its domain, and S2 is an isometry on its domain. And then we can just pop them back together because, once again, U is in the range of the root, and W is in the orthogonal complement of the range of the root. So that's by Pythagoras again. And then that's what V was. Okay, so then the last thing to check, finally, is that we get the right thing if we compose S and root T star T. So if we apply root T star T to V and then apply S to that, then let's see. Well, first off, S2 doesn't even enter into it because now we're just looking at S applied to the range. So this is S1 applied to the same thing. Yeah, okay, so maybe plus 0 for the part that's in the orthogonal complement of the range of the root. And then let's see. So now how is S1 defined? Well, it's defined to be T of V. And so curiously, that does it. So T is S root T star T as required. And we win, get a big box for that one because that was a lot of work. Okay, so this is a nice example of why we talk about the theory of linear operators. So in math, mathematicians like to talk about the theory of this or the theory of that, but you can really see like we have built up a whole lot. Like the contents of the proof of this theorem reference like stuff from all throughout the book, stuff about, adjoints and inner products and orthogonality and orthogonal complements and this and that, and all kinds of stuff to bring together this idea that this identity of that T can be written as these, a generic operator can be written in terms of these two very precise things, this unitary or isometry operator, and then this positive one, and that it has this form that's very similar to what we see by analogy with the complex numbers. And so this is also kind of an example of what happens a lot when you're looking at linear operators is you have the proof, and the proof is hairy and technical and involves checking a whole bunch of things match up and so on and so forth. But then what it gives you when you're done is just this algebraic tool that you can use just purely formally to get a lot of mileage out of for understanding the structure of other things.